Hey everyone, my name is Martin Koistinen. I'm not a professional YouTuber. I don't have very good audio equipment. I apologize for the audio up front. I'm making this video because I've recently got into 3D printing. I received my Prusa i3 Mark III's back in February. It was like one of the first ones, one of the first new ones, which was great. And I've been loving it. I've really been enjoying 3D printing, and I've been consuming videos from YouTube from many of you, Devin, Angus, Tom, Joel, especially all of you. Thank you very much. You've really helped me get a lot out of my printer in such a short time. And for me, using a 3D printer is cool in its own right, but I get an extra bit of joy by designing something in a program like Fusion 360 and then being able to hold it in your hand. I really enjoy that. It's just so cool to think of something and make it happen. I think it's a great feedback loop. Anyway, since I've been absorbing so much content from YouTubers in the area of this topic, I thought I would like to give back a little bit. So I made this model. I've had a few models here on Thingiverse that I've worked on over the last couple of months, but this is a really simple one. And yes, I'm going to happily share this with everybody, but the thing I'm going to give back here is a little bit, it's a technique that I've learned, figured out kind of in Fusion 360, and I'm absolutely sure the smart people at Autodesk built this into the program intentionally, but nonetheless, I haven't seen anybody talk about it, this technique, and I wanted to share it back. I mean, I know it's only been 2 months, but I've really been voraciously learning as much as I can about it, and I haven't seen this anywhere. So maybe some of you haven't either. Nonetheless, here it is. So just a quick overview of the project is a pushpin fridge magnet. Basically, it looks like your typical pushpin, which normally would have a pin sticking out. You stick it on your corkboard to hold notes and such down. I wanted to have the familiar pushpin shape, but for refrigerator magnets. So I ordered some magnets off of Amazon, and I designed this piece to kind of go around it and be embedded inside of it. And I printed a number of them off, and they worked great. When I ordered the magnets, the dimensions were stated, but the picture didn't seem to match the proportions that they were stating the dimensions to be. So I was a little bit nervous about that as I started modeling this before they even arrived. And so that kind of helped me prepare what I'm doing a little bit differently. So let's jump into the Fusion 360 model. So this is it. As you can see, it looks like a pushpin, right? It's a little bit larger than a normal pushpin, which is about 1 centimeter across the base, and a little bit more for the height. But here it is, you know, it's extra large. This is a cross section just so you can see how basically it works. So it's just a bunch of PLA or PETG, I guess, and there's a cavity here where I will insert a magnet. So I've modified my G code to stop when it gets to this point here, and then I just basically push in the magnet, and then I let it resume, and then it fills up, you know, it builds the rest of the push pin, and it works great. I've got about a dozen of them on my refrigerator now. The cool thing about this model is that it's small and quick. It's about 1 gram of filament, and when I get close to the end of a roll of some color, I'll just print off a couple of these until it's gone, and add it to my refrigerator collection. Anyway, so the interesting part is not all that. The interesting part, I think, is, I'm just turning this off, and we're going to go to the sketch and edit the sketch. Okay, here we go. So basically, I did this twice, as you can see, and I'm going to show you why in a moment. So basically, I started here, like any other good, you know, Angus taught me well to make sure that everything's locked firmly in space. And so this was originally on my origin right here, and I made sure I had dimensions for everything, and it was, you know, I had perpendicular constraints and horizontal and vertical constraints, et cetera, as I needed, and it worked, right? It all was black, and everything was fine. But then I quickly realized, just so you know, all these dimensions came from my micrometer measuring an actual pushpin. So I feel confident that this is going to produce the right shape, and as you just saw, it does. But the problem is that the actual part is only just a hair wider than the actual magnets that I ordered. So this magnet is going to be about this big. It's a centimeter in diameter, or 5 millimeters in radius, and 3 millimeters in height. So it's really going to struggle to fit in this space. In fact, it can't. And so I knew I was going to have to make it larger, and I was prepared for that from the outset. But the question is, how much? How much larger does it need to be in order to fit the magnet? So what I could have done is I could have maybe drawn a magnet proportioned cavity in here into the profile, and then measured what Fusion 360 thinks it is, and then I know what it should be, and then I can determine a factor, and I can go back and I can multiply all these by that factor. That seems like a lot of work to me, so I wanted to do it differently. So basically what I did is I just moved the whole thing over and left it here as kind of a notepad. And when I did that, of course, this wasn't initially fixed using a fixed constraint, and so everything turned blue. But this is supposed to be on the origin, and if it was, it would all be black. So I went ahead and fixed this. Apologies to Angus. But I think this is actually a pretty good use case. This profile is not going to be used in the Revolve. It's only here for reference. So I basically built the same thing again over here, and you can see that it's not black, it's blue, and I also have the cavity here for the magnet. But there's also a lot of angles here, whereas this one doesn't have that. Well, why is that? The reason is because I knew that what I needed here was a projection of this over here that could scale, right? So I don't care about the actual scale of this. I care that it stays in proportion to an actual pushpin, because that's what us humans recognize as a pushpin, is the shape of it, not necessarily the scale of it. I guess you could argue that we need both, but nonetheless, the shape of this is what I was after, and I knew that the scale had to change. So as you can see, I just scaled it up. This is a blue line indicating it's not fixed. It would float, as I just did, by pulling on this point. So how did I do that? How did I make it a projection of this? So, I mean, I can't change the proportions of this by moving these points around. I can only change the scale. Well, the way I did that is with these angles, which I'm defining. So instead of defining the length of the sides of all of these facets, I'm defining the angles to the major points between them, okay? So that, I think, is the novel thing, and I say novel loosely here because I'm sure that 360 professionals are doing this all the time. So what I did is I drew out a cavity that is going to be my magnet. I don't know, when I was doing this, I didn't know exactly how big it would be, so I didn't care. I just made it a rectangle. But I did know that I didn't want it any closer than 3 filament layers off the build plate. So in this case, that's 0.4 millimeters, because the first layer on my Prusa is, well, at least from my slicer software, is almost always 0.2 millimeters. I guess I could change that, but I'm not going to. And then I had 2 additional layers at the layer height of 0.1 millimeters layer height, so that comes out to 4/10 of a millimeter as my distance. And I chose 3 layers because I think that's going to be strong enough that it won't rip out at the bottom because of the strong magnet force on my refrigerator, and also thin enough that I can get enough traction to the metal to hold things down like photographs and such. The other thing I knew I needed was to make sure that I had enough distance between the cavity for the magnet and this arc here. Now remember that I'm going to basically be printing this up to this level and then stopping it and pushing the magnet in, and then it's going to resume. So that means there's not really anything holding all of this down. I'm counting on the amount of material here, or more appropriately here, to keep the top and the bottom connected. And I know that this 1 millimeter is good because I've already printed a couple of these and I've tried to tear them apart, and whenever I do, they break usually up here in the stem, not here. So I know that 1 millimeter is sufficient to give it the strength it needs. So what do we have? We have this thing defined with a bunch of angles, and we have this cavity, which is arbitrary right now, but we have a constraint that this is no closer than 1 millimeter and a constraint that this is no closer than 0.4 millimeters from the build plate. How did I make these angles? Well, I remember from high school geometry that the tangent of an angle is the ratio between the length of the opposite side and the length of the adjacent side of the triangle. So from here to here, the tangent of this angle is going to be this distance, sometimes called the rise of the angle, divided by the run, or this length here of the angle. And I have those dimensions right here, right? So even though this is a different size now, they are similar in proportions, and therefore all these angles would be the same. So I know that this angle here would be, the tangent of that angle would be the height of 3.6 millimeters divided by the width or the run of 5.1 millimeters. So I can actually go in here and I can actually just reference those numbers. So if I open this up, I can type in ATAN, and then I can, well, let me just do it. So ATAN for arctangent, or the inverse of the tangent, and then I can click on the rise, and then I can click divided by, and click on the run, and boom, I've got the right angle. Let me rephrase that. I've got the correct angle. It's not a, well, it is a right angle, but this is not the right angle part. Nonetheless, this is the correct angle for this point here, which determines, obviously, this 3-point arc. And I did the same exercise for these others. Now, for most of the others, I actually typed in the numbers. I didn't reference them because I don't expect to be remeasuring and coming up with new measurements for my my pushpin shape. But I mean, I could, and it might be smart for me to do it this method where I'm actually referencing these measurements. But I went ahead and typed them into this. So I did this one, this one, this one, this one. And then I also did, using this as an origin, the angle to here, the angle to here, and the angle to here. And then I made sure that all the horizontal and vertical lines are indeed marked with constraints to make them horizontal or vertical. The only thing that remains is this right here, and I went ahead and used this as an origin and marked that angle as well, using the measurements, the rise, which I think I actually typed in the formula for that. So my machine's running really slow because I'm recording. Yeah, so as you can see, it's 10.2 minus 3.6, which makes sense. It's this whole distance minus this distance represents this distance, divided by the difference between this and this, which is 0.5, if I'm not mistaken. Yeah. So, yeah. So anyway, I've got all of these angles declared, and that makes this whole thing scale but not lose its shape, because it's basically a projection of this shape onto this using angles. Now, to create this minimum distance here, I'm going to zoom in a little bit. What I did is I used this center point of this. This is a circular, this is a 3-point arc, which was constrained as which is tangent to the vertical. So when you do a 3-point arc in Fusion 360, it will create for you a reference or construction point for the center of that arc, if this was a whole circle. And so to make this minimum distance, I drew a construction line from here to the corner of my magnet cavity. And then I drew another line from there to the arc, and I made sure that it was parallel to the first. So effectively, this is one line, which represents a radius of this greater circle, right? So because of that, we know that the distance from here to here, if we set it to 1 millimeter, that is the closest that this point will ever be to this arc, right? That's how we know that. So that serves as a useful geometry, I guess, for doing that. Okay, so now we have this projection. We have our constraints of being 0.4 millimeters off the build plate and 1 millimeter away from the edge of this arc. Only thing left to do is to provide the measurements of this cavity. So I did receive the magnets, obviously, from Amazon, and I did measure them with my micrometer, and lo and behold, they actually came out to the size that they said, which in this case is, type it in. 3 millimeters. My machine's going pretty slow. 3 millimeters. I'm going to add 0.1 millimeter tolerance. In my case, my printer is very accurate, and maybe 0.2 will be better for some people, but for me it's 0.1. And I'm going to declare that to be my height, and you can see already that's going to affect the shape, or the size, sorry, the scale of this whole profile. And we're going to do the same thing for the radius of the magnet, or half the diameter. In this case, I know it to be 5 millimeters, and plus I'm going to add the same tolerance of 0.1 to it. 5.1, return. And you can see again, it will change the scale of this diagram. Now, I don't know what's going on, but for some reason, Fusion still hasn't made these black, and I don't really know why, because it is fixed in space now. Earlier it was painting it black. I think I can trick it by just creating a line that goes from here to here, and then it will lock everything in. But the thing is, that's not needed, and I can delete it. It's just, I love Fusion 360, I really do, but I have to say its performance on a Mac is a little bit lackluster. I'll delete. Okay, so I've deleted that line again, and you can see that it's all black. There's nothing undetermined in that profile. And now I know that this cavity, which is big enough to hold the magnets, is the determines the size of this pushpin, and I know that the pushpin is the smallest pushpin I need to hold this magnet with a constraint of 1 millimeter here and 0.4 millimeters off the build plate. So stop sketch and let's look at our work. There it is. So that is what I wanted to share with you guys. I know it's not, novel in the fact that I'm using constraints. I think Angus has done a great job of helping me and others understand constraints in Fusion 360. I think the novel part of this, and again, I know that other people probably use it, I just haven't seen it anywhere, is using determined angles to create a projection of a shape rather than a fixed, number of sides and lengths of sides. I hope that helps you in future modeling. And I'm going to share this Fusion 360 archive onto this Thingiverse page. I'll put the links in the description. So if you want to make your own pushpin magnet, or you have another project that's similar, and maybe you have different, different source of magnets and therefore a different size, or maybe you have some magnets lying around that you want to use. They already have a specific size. Then you'll know how to use this archive and where to put the numbers and why it works the way it works. So anyway, I hope that's just me sharing, giving back to the community, which I've grown to love. I wish you all the best in your 3D printing.